Bright Tuty. Every student matters.
So now, let us see how this sound travels. This sound reaches our ears. How actually it is reaching our ears, that is very, very important to understand. We have seen till now that it is the vibrations caused which produce sound. Now, what exactly these vibrations cause and how these vibrations reach our ear? Let us take an example of the tuning fork. When we just try to hit the tuning fork and now the tuning fork is moving. Now what happens is, just taking an example that here I am standing at point A. Now in between my ear and the tuning fork, this is the atmosphere, this is the air which is present. Now when the air is normally there, then in that case it is in equilibrium state, means the particles are consistently, properly, with normal and equal density, these particles are distributed in the air. But when sound is produced, what happens is that this tuning fork, when it moves ahead a bit, then these air particles, it pushes the air particles, right? So these air particles, they get compressed a bit. Now when they get compressed, now there is this particular region where we see that the air particles now will come a bit closer to each other than normal, right? Then when these particles compress, they will exert pressure on the particles ahead of them. Fine. And after pushing those particles, they will come back to their normal position. So what happens is, now the next particles, the next layer, that will be compressed. Fine. Again these particles when compressed, they will exert pressure ahead, and so this is the kind of movement they will be producing. The particles of air, they will exert pressure on the particles ahead of them, and after hitting them and making them a bit compressed, they will come back to their normal position. So this is the kind of to and fro motion the particles will be showing. All the particles, they will be showing these to and fro motion till they reach me, till they reach my ear. Got it? And this is how this vibratory disturbance caused by this tuning fork, it actually led to the production of sound which reaches my ear. Now very important part is the momentarily increase in the density of this particular part. Increase in density means now the particles are closer to each other as compared to the normal. This particular part is known as compression. So what is compression? Compression is that part of air where the particles are comparatively closer to each other as compared to the normal arrangement. Fine. And the particles where there is a reduction in the density of the air or the particles, that part is known as rarefaction. I repeat, that is known as rarefaction. So when we talk about the sound, this sound has alternate compression and rarefaction, means one part will be compressed, the other part will be a bit elongated one. So this is compression part, this is rarefaction, again compression, again rarefaction. That is why we have said that this is alternative, right? So how will we define this compression and rarefaction? Compression is that part of the sound or the air where the particles are closer to each other, and because the particles are closer in that particular limited area, that is why the density increases in compression, and because the particles are closer, they will be exerting high pressure. So the compression part is a region of high pressure as compared to the rarefaction. Now what is rarefaction? It is that part of the air or the layer of the air in which the particles are apart from each other as compared to the normal arrangement, because of which the density is less than the normal, and because of less density, the particles being apart from each other at some distance, they will exert lesser pressure. Got it? Fine. So this is compression and rarefaction. Now please try to relate it through this representation. We will do an activity in which we will take a slinky. Now what exactly is a slinky? You must be knowing it. I repeat. Now what exactly is a slinky? You must be knowing it. It is a long elastic spring which can be easily compressed or extended. Now what we will do is, we will ask one of our friend to hold one part of this particular slinky, and from the other part what I'll do is, I'll try to compress or I'll try to pull this slinky. Fine. Now when we observe what happened when I applied the force in either of these two directions, what I saw is this kind of representation, that in this slinky, when it was a normal case, right, in part A we see that there is a uniformity between the distances of these particular turns, but when I extended it or I pulled it up, then in that case what happened was, there was a region where these turns, they come closer to each other, then it will be apart from each other, closer to each other, apart, and alternatively we will see this kind of arrangement. This C part or the compression part, as we know that the particles where come closer to each other, same is the case with the slinky, the turns are closer to each other. As compared to the normal, we can see this is quite compact, and this is the rarefaction part, which is as compared to the normal, this is basically the turns are a bit apart from each other. So this is, through a slinky we can show how formation of compression and rarefaction takes place. Got it? Fine. Now let us try to relate in the case of density variations. When the speaker is speaking something, then the air representation will be like this. The air particles under compression part will be closer to each other, then they are apart from each other, rarefaction part closer, compression part, rarefaction apart from each other, and so on, right? And in these compressions we have said that the pressure will be increased. Therefore if we try to relate the pressure variations, then in the compression part the pressure will be more because the area is less. Otherwise also you have studied pressure, that what exactly was the way of calculating pressure? It was equal to force per unit area. If the area is less, it is in denominator, the inverse effect will be there on pressure, which will be high. So if less area is there, pressure will be increased, and if it is more area, pressure will be decreased. So this is as per pressure. Fine. Now this to and fro motion of the particles can be represented in the form of a wave. Now what exactly is a wave? Wave is a vibratory disturbance in any particular medium. So first of all we will try to relate what is a wave. Wave is a vibratory disturbance in any medium. Now because I have used the term medium, so first of all I would like to relate what exactly is meant by medium. Now what is medium? Medium basically is related as the matter or the substance through which sound moves or travels, right? So this medium is the mass or the substance, the matter in which sound is traveling. This medium may be solid, this medium may be liquid, this medium may be a gas. Sound travels in all the three medium, solid, liquid and gas, and it travels in the form of a vibratory disturbance. That vibratory disturbance is known as a wave. We have already seen how these waves travel. How they travel? The particles of the medium which are in contact with this particular vibrating object, they first displace from their original equilibrium state, then they exert pressure on the particles ahead of them and come back to their normal. Now the next particles on which this pressure was exerted, again they will do the same, and this is how the vibratory motion will reach our ears. But one important thing we need to relate is that the particles are just moving to and fro in their positions only. The particles are not actually traveling. When we talk about a vibratory disturbance, that vibratory disturbance is leading to only the movement of particles in to and fro direction. The particles are not moving along with sound, right? The vibration is carried. So when we talk about a wave carries energy only, it does not carry mass or it does not carry the particles along with it. Fine. So if we see the graphical representation of sound waves, now this is quite important. First thing we need to remember is that sound travels in the form of vibratory motion or disturbance, which is known as wave. So we can use the term sound waves. Now when we talk about sound waves, then when we represent it graphically, it is the density or the pressure. Fine. The density of the air particles that we have seen under compression and rarefaction, or the pressure exerted by the particles, and next is the distance travelled. So when we try to relate it in a graph, that is distance and density graph. This is the distance density graph, right, or distance pressure graph. Then we relate wave like this motion, and this line is actually the middle average density or average pressure line, right. So this is the average density or average pressure line. Fine. Now the crest part or the hump or the region above this average density shows that the density is increasing, whereas this depression or the trough part, that is basically showing the density or pressure less than the normal. So this is the graphical representation how we can represent a sound wave. Got it?